Hello, welcome to CE 3305, lesson 9, and this is the component dealing with momentum, and in this particular case, we're now discussing angular momentum. Now, angular momentum is used when things are rotating, and the conservation of angular momentum, also known as the moment of momentum, is used to explain how forces cause rotation and or how forces cause rotation or how rotation is stopped by applying a force. And it's a fundamental concept in things like pumps and similar machines. In terms of the Reynolds transport theorem, the extensive property of angular momentum is mass multiplied by r cross v, where this is the vector product of the two vectors r and v. You remember back in your calculus classes how the cross product would have been in Cartesian. They probably taught a formula ijk, and then rx, ry, rz, vx, vy, vz, that tableau, and then you did the crisscross terms to go ahead and recover the vector output. That's the extensive component, angular momentum. Now we want to express it in terms of intensive properties. So the intensive property per unit mass is simply the m over m term, which when it's implemented leaves behind the r cross v. The intensive angular momentum per unit volume, which is what we want to use in our Reynolds transport theorem, is rho multiplied by r cross v. So this is the part that in the Reynolds transport theorem is going to replace the beta rho dv in the volume term and the beta rho v dot dA in the flux terms. The beta is this thing, or I guess the beta per rho. So if we apply the Reynolds transport theorem as described in the book, and we've done before, we are going to start with a system equation. D by dt of m r cross v is equal to r cross f. So that we got from system mechanics, back from our other kinematics in our other engineering classes. This is essentially the sum of the moments is equal to r cross f from ordinary engineering mechanics, and this term here and sum of the moments are the same thing. When we apply the Reynolds transport theorem, we'll obtain the integral form as the sum of r cross f is equal to d by dt of rho r cross v d volume integrated over the control volume plus rho r cross v times v dot dA integrated over the control surface. This second term will be evaluated by a mixed triple product. When we do the calculus. Just a quick reminder of some ideas. Remember back in ordinary mechanics, this is the mass, and it has some velocity headed that way, and we have some point of rotation, then the lever arm multiplied by the velocity gives us the angular rotation. We have r times omega is the velocity. The mass times the velocity is the mass times r dot omega. Omega is the angular speed. This is the distance. The combination of all three is the momentum, and all we're doing with Reynolds transport theorem is equating the time rate of change of the mr omega term that has an m dr dt plus times omega plus an mr d omega dt, and you notice the mass doesn't get differentiated with time because we're starting with a constant mass. So what we're going to do here is just do this by an example problem. The application of angular momentum usually involves continuity and Bernoulli's equation or some kind of energy equation. Selecting the control volume itself is important. We're going to do an example where we have a control volume that first moves, and then I'll repeat the example with a control volume fixed in space, and I think you'll immediately see the ease of a clever control volume choice. So, we're asked to determine the power provided by a simple reaction turbine that rotates in a horizontal plane at 500 revolutions per minute. Water enters from a vertical center pivot, so the water's entering here, and then it goes out the two arms and then creates jets, and the reaction of the jets causes rotation. And it exits through these nozzles. Each of the nozzles in this particular example has a cross-sectional area of 10 centimeters squared, and the total discharge, the Q through the whole system, is 0.1 cubic meters per second. And we want to determine the power that's produced. So we put the water in, this thing's going to spin around. At some point it hits some constant angular velocity of 500 revolutions per minute. We know the flow rate. Presumably we're going to divide that by 2 and send 1/2 of the flow rate down each arm. We know the distance from the pivot to the center of the jet. And we know the cross-sectional areas of the jet. Okay, so center pivot irrigation or a rainbird or something like that. Okay, so if we were going to beat this with our usual, all right, zoomed in a little bit. Okay, if we're going to do this with our usual procedure, I've listed or at least stated the problem. We have the sketch. I showed you the knowns and the unknowns, and then we would start with continuity. But wait, there's more. First, we would establish a control volume, and it's done here. And we can have the control volume as essentially the volume of the rainbird, and we're going to allow this control volume to rotate. Okay, at each end, we have a velocity of the jet, an outward pointing area vector, velocity of the jet, outward pointing area vector, and I'm defining a coordinate system that is radial and along the arm, and then a tangential component which is at a right angle to the arm, and this point here is rotating at 500 RPM, and it's a 1/2 meter away from the axis of rotation. Okay, so all that information will become important as we proceed with the analysis. Okay, so if we apply continuity, we have 0 equals d by dt of rho dv plus the integral of the control surface of rho v dot dA. This term right here zeroes out. Non-deforming control volume. This thing is having trouble with autofocus today. Constant density. And all that's left is the flux integral. So we have 0 is equal to minus rho q in. So that's the mass flow going into the object, plus rho velocity jet, area jet for one of the jets, plus rho velocity jet, area jet for the other jet. The reason those are plus is the velocity and the area are pointing in the same direction for either of the jets. Okay, so the velocity of the jet is the velocity relative to the control volume. That will have some significance later on. Okay, so the discharge divided by 2 equals velocity of jet, area of the jet. That's what we're going to get out of continuity. And the velocity of the jet is therefore a qn over 2 area jet, which is 0.1 meters cubed per second divided by 2 times 10 centimeters squared times 1 over 100 centimeters squared, and the result is 50 meters per second, which is actually a pretty substantial velocity. I wouldn't want to put my face in front of that. Okay, next we're going to apply angular momentum, and we have the sum of r cross f equals d by dt of r cross v rho dv plus the integral over the control surface of rho of r cross v rho v dot dA. So that's just direct, essentially blind application of Reynolds transport theorem. And we're going to apply the momentum relative to this point where things are rotating. So r, our r vector, is equal to cap r, whatever this length is, in the r direction. So that's what this symbol or this notation is showing. And r cross v, in this case, is here's the velocity of the jet, and then here's the velocity of the fixed point. The velocity of the fixed point is equal to whatever the velocity of the control volume is, multiplied or plus whatever the velocity of the jet is, which happens to equal omega times r minus the velocity of the jet in the tangential direction, and r is r in the r direction. And when we perform the cross product, what we have left is omega r squared minus r velocity of the jet. Oh, that's better. Okay. Continuing with the analysis, so we've determined what r cross v is in the prior page, and now we'll go ahead and insert those into the various parts of the formula. We have d by dt, and this term right here is the integral from 0 to capital R of r cross v rho dv, and this term right here is the integral from minus r to 0 of r cross v rho dv. So this is the upper arm, and this is the lower arm. And so we have d by dt rho omega r squared, area of the jet, divided by 3, minus rho r squared, velocity of jet, area jet, divided by 2 for the upper arm. The lower arm is a minus d by dt rho omega r cubed, area jet over 3, minus rho r squared, velocity jet, area jet over 2. Here we notice that this entire term and that entire term are identical, but of opposite sides, so they cancel. The flux terms, the upper arm flux is minus rho q over 2, capital R times velocity jet minus omega r in the k-axis, minus rho q over 2, cap r, velocity jet minus omega r in the k-axis. And so what's left is r cross f equals minus rho q r, velocity of jet minus omega r k. Now, r cross f is the definition of torque, and so the torque is rho qr times the quantity velocity jet minus omega r, and the reaction torque is the torque of the generator on the arms. Therefore, the torque of the arms on the generator is equal and opposite, which is rho qr velocity jet minus omega cap r. And at this point, we could substitute in numerical values, which we'll do in a second. And if we recall, power is work over time, which is force times distance over time. Distance over time is velocity, so force times velocity would give us the ability to determine power. If we look at the torque term is force. This part of the term is force, and then r is the distance. R times omega is distance over time, Therefore, the power is equal to the torque multiplied by the angular velocity, or the angular frequency. In our case, rho q velocity of jet cap r omega minus rho q omega squared cap r squared. Now when we substitute in numerical values, rho 1,000 kilograms per meter cubed, 0.1 meters cubed per second for q, 50 meters per second for the velocity of the jet, 0.5 meters for the radial arm distance, times 500 times 2 pi divided by 60, that's to convert our angular frequency into radians per second, equals 62.36 kilonewton meters per second, which is 62, rounded up, 0.4 kilowatts. Okay, so that's how to do it with a moving control volume. For the sake of argument and completeness, let's just go ahead and assume we want to attack the same problem with just an arbitrary system. And this is going to take a little bit. I'm going to have to zoom in and adjust the camera a touch. Okay, so we're going to be, I'll be zooming in and out in this case. Okay, so let's consider the same problem, this time in an inertial reference frame, rather than a reference frame that's moving with the, well, the reference frame's still moving, it's just a little bit more complicated here. That works better. Let's get some focus going. No, that's not good enough. Okay, if we do that, continuity won't change much for us. We will ultimately deduce that the jet velocity is 50 meters per second. However, here's what our coordinate system looks like. We have x and y is drawn here, and we have this object which is spinning in that coordinate system, and at any instant it has an angle theta, and it has these velocities of the jets located here, and this thing just spins around with a speed of d theta dt. Okay, what that does is it slightly changes our r cross f equals d by dt control volume. Reynolds transport theorem doesn't change. But what does change is how each of the terms are inferred. So here's a sketch of our system at any instant in time. Wherever this arm is, there's an angle theta, another angle theta. We have a radial component of velocity, a tangential component of velocity of the arm, and we have our jet velocity of the jet. We know that the velocity tangential, or what I'm calling velocity in the theta direction, is r times omega. That's how fast that arm is moving. And we know the numerical velocity of the jet. And that's used to construct these two parametric equations. R cosine theta I minus r sine theta j gives us the r vector. And v sub r cosine theta I minus r omega sine theta I plus v sub r sine theta j minus r omega cosine theta j gives us the velocity vector, where vr is the relative velocity. So that's whatever, the radial velocity and the tangential component. So now we set the d by dt over the control volume of r cross v rho dv is d by dt of r cross v rho dv plus, this is for the upper arm and the lower arm. And now let's look at r cross v when we go ahead and represent it with these Cartesian coordinates. So we have to evaluate r cross v and the ijk, the r component, the v component, and when we go ahead and perform the various multiplications, you probably remember this from Crisscross World. the I component has zeros in it, the j component has zeros in it. The only thing that has non-zero in this case is the k component, so we have r squared omega k. And when we evaluate those, do the upper arm, we have the same case as before because we're evaluating from 0 to r and from 0 to minus r. They cancel. But we still have the flux term. So in the flux term, we have the same definition of r in velocity, r cosine theta I, r sine theta j, velocity of jet sine I minus r omega sine theta I plus r omega cosine theta j minus velocity jet cosine theta j. And here's our drawing for our velocity of the jet and then the velocity of this point. Now we have to do r cross v. Same thing as before. The I is a 0, and going back there's a 0, so nothing in the I. J has a 0 that way. J has a 0 coming that way, nothing in the J. But the K term has the non-zero components. So the result is r cosine theta times the quantity r omega cosine theta minus velocity jet cosine theta minus r sine theta, quantity velocity jet sine theta minus r omega sine theta k. We'll examine the trigonometric identities and discover we can factor out a cosine squared and a sine squared. And then we have an r squared omega minus r velocity of jet. When we do that factoring, we have cosine squared plus sine squared times r squared omega minus r velocity of jet. Cosine squared sine squared, if you recall from your trigonometric identities, is equal to 1. And so finally what's left, r cross v, is r squared omega minus r velocity of jet k. When we evaluate the control surface integrals, we have the upper arm integral, the lower arm integral, and at this point the analysis is identical to before. So choice of a coordinate system, we basically did identical analysis, but a moving coordinate system simplifies this part. The r cross v can almost be done by visual inspection. Okay, so that completes the application of angular velocity. Problems involving angular velocity can get, they're not hard, but they can get quite long because of the necessity to carefully keep track of the various vector terms. Okay, that completes the video. Thank you for your attention and have a great day.